Hi, everyone. Welcome to Protocol Lab's Research Seminar Series. Today's speaker is Anca Nitulescu. Anca received their PhD from ENS Paris under the supervision of David Poincheval, as well as Dario Fiore from MDA Madrid. Their PhD work focused on succinct, non-interactive arguments of knowledge, or SNARKs, a tool to prove integrity for results of delegated computation. They were a visiting assistant researcher at Columbia University, and they worked with Rosario Gennaro and Maria Rykova on verifiable computation topics. They also completed a postdoc at Aarhus University on topics related to authentication primitives and theoretical aspects of SNARKs. Their main research interests are cryptographic proving systems, especially zero-knowledge proofs and SNARKs. Their talk today is on verifiable computation over encrypted data. Anca, I'll let you take it from here.
Yeah, thank you for the kind introduction. So, sure, I will talk about some line of research that interested me recently, and this is verifiable computation on encrypted data. And as I always like to start with some motivational tale, today it's about the bare necessities of a cloud user. And we have the following characters. So here is Baloo, the client, who is a usual internet user, which of course has a laptop, a smartphone, but has limited storage, a minimal operation system, maybe limited computational power. So he is very likely to use cloud services to delegate the storage. And here is some cloud provider, Mowgli, who is offering his remote storage, maybe computational power, network, and other services like software or whatever remote service Baloo needs. So this is very practical. Let's see really a use case in the area of biometric surveillance systems. Here we have Baloo delegating its medical personal data to the cloud. So this will be stored during months, years, like long-term storage. And regularly, Baloo will require for the server to compute some algorithm on this data in order to receive some diagnosis. So to learn what kind of medical condition he is in. The server has computational power, so it can compute all this, or it stores all the data. So Baloo has only to retrieve the result, and he's very happy with his diagnosis when he's healthy, of course. So there are many benefits in such an outsource of computation and of data, but this comes at a cost, and there are risks to encounter in this remote scenario. So for example, the server may be untrusted. All the data is stored there, like in clear, and also computation. So first threat will be that the confidential data of Baloo will be stolen or exposed. Like a hacker attacks the server, that something can get wrong there. Also, how can Baloo trust the integrity or the correctness of the results he receives from the server? So he has diagnoses, but those are not guaranteed to be correctly computed on its data. So corruption on the computation is also possible in this scenario. So here comes the crypto to solve these kind of threats. And we have the common solution for privacy of data is encryption. So we will ask Baloo to first encrypt the data to stay safe, and the server will just store this encryption. But classical ciphertexts are not malleable. So server cannot compute this kind of computation Baloo really wants to have. Meaning that we need some more advanced encryption schemes, and those are fully homomorphic encryption schemes that have an extra property of malleability of data. So we can compute a function on ciphertext and obtain encrypted results. So we have privacy not only for the inputs, but also for the outputs. And there is a long line of work that builds this kind of schemes. They are not really super efficient, up to date, but they are usable in practice. And a lot of research is ongoing on this. For the second problem Baloo had with the integrity of computation, we also have cryptographic primitives that solved it. It's notably verifiable computation, which is the subject of my talk today. So what this is, it's actually asking from the server, from the one who computes on data, an extra proof. So these are proof systems, usually, which guarantees to Baloo that the computation was done correctly. And some proof systems really adapted for Baloo, for very lazy clients, are snarks, which require very little communication. So proofs are constant side or very short, and no interaction between servers. The server just sends the result together with a proof, no other interaction. And the verification is a lot more efficient than computing on data, recomputing the function itself. So this is the interest of outsourcing computation, to have the results and fast verification. And we can have an extra feature, which is very common in proof system, zero knowledge, meaning that we also protect the intermediate steps and the algorithm privacy of the prover. So the server mogli can have some secret parameters, which are intellectual property, that he wants not to communicate to Baloo, but of course we can verify the statement is correct without learning anything else about the proof. This is called zero knowledge. And there is a long line of work that constructs verifiable computation schemes, and notably snarks. But what we really dream of is to have a full solution to our outsourcing computation and data problem. And full solution means that we need also privacy for the data and verifiability for the results. So we will ideally like to plug verifiable computation on top of computation over encrypted data. So on top of fully homomorphic encryption. And this is not trivial, and there are a lot of challenges here. So we will discover them together during today's talk. So this being said, I'm going to just have an overlook of what I will present today. First, I will try to dive you into the small secrets of snarks, but maybe it's a very high level intuition and overview of these schemes and some history of proof systems. Then talk about the challenges on adding privacy to verifiable computation, show some constructions. So the result I am presenting today, the main result, and conclude together maybe with open questions. So let's start with some snark intuition and details. So in snarks, we have two actors. The same as before, we will call Baloo the verifier. He wants to get convinced that the statement is true. And Mowgli will be the prover, who actually computes on data and has the witness to some statement, to its claim. Okay, so as we said, these are proof systems where we don't only ask for a computation, but also for a proof that convinces us that everything happens correctly. So this is a valid statement. And of course, as I said, we start with the easy scenario with the very well-known construction, which guarantee no confidentiality of the data. The data is stored, like the inputs of the computation are visible to the prover and to the verifier. Nothing is encrypted, right? So a bit of history. Proof systems were introduced in crypto in the early 80s. But we had the first succinct and this kind of short and efficient proof system in the 90s by the protocol of Kellyanne. And this will be like the first step towards snarks construction. And this protocol is interactive. So verifier will engage with a prover into an exchange of question and answer kind of protocol. So Baloo asks his question, he gets his answer. Depending on this answer, it can adapt and ask another question and so on, until he gets convinced or not that the statement is valid. So the next step will be to make this protocol non-interactive. We don't want to have this kind of communication between prover and verifier. So we would like the prover just to send the answers to the questions. So of course, if the questions are generated by the prover and are controlled by the prover, then we always can pick the question that we know how to answer. So they should be independent of the prover. And this is made with some heuristic, which is called random oracle. So having access to a source of randomness that is independent from the prover, it's not controlled by the prover, we can generate this, simulate these questions and have the answers as an only reply. And the proof is actually the answers, and also Baloo will use this random oracle in order to verify the proof. So this is the random oracle model where Mikaeli achieved the first non-interactive kind of snark protocol. It was still inefficient, but what it is useful to? So in these centralized settings, this fact that the prover doesn't have to anticipate who is verifying and doesn't have to engage into a exchange with a verifier, the fact that the proof is independent of the verifier, so it's publicly verifiable, is very useful. For example, in blockchains, if a prover claims a new block, the verifiers are able to just check if this is a correct or not claim. So this is why we really search for non-interactive proof system. So another flavor of non-interactive proof system, which are even constant size and are not in this random oracle, they are not using this kind of model. It's they are defined on pairing-based groups usually, and they use this kind of common referencing. So CRS here holds from common referencing, and we will call them pre-processing snarks, or because they are a one-round protocol. But one round in what sense? The common reference string is a piece of information independent of future statements and proofs that is given by, for example, by the verifier to the prover once, forever, and then the prover can use it to generate many proofs for many different statements. So it's not really an interactive protocol, but it has some trusted piece of information that should be generated ahead of time. And of course, if we want zero knowledge, we should not leave the verifier to decide on common referencing. We need a trusted party who generates this. So this is a trusted setup, and there are some drawbacks here to having such a thing in practice. So pre-processing requires secret coins. It's quite expensive. It needs to gather together trusted parties and to make a ceremony. And it can be subject to subversion. So there are works that study what happens when someone keeps the trapdoor to such a generation of CRS, or this is not correctly generated according to the specification. So these are the drawbacks maybe, but it's also giving us very efficient snarks. And I have a disclaimer here. This efficiency and constant size proofs are not coming for free. So we have the cost of some strong assumptions. The assumptions are known as non-falsifiable assumptions or knowledge assumptions. And they are stronger than classical crypto assumptions. So this was specified by the result of Gentry and which was, this result shows that if we want to construct a snark with a proof independent of the size of the witness, like a big computation, means that we need this non-falsifiable assumption. Okay, great. We accept this. So we have many constructions. So some of the popular snarks were based on this power knowledge of exponent assumption, and they were designed in the 2013. The one who has implementation is Pinocchio. Then there was a more generic way to construct snarks from linear interactive proofs under some extractable collision-resistant hash assumption. And maybe the one that we like the most, and we use at Protocol Labs, is GROT16, which is based on some generic group assumption. This is a idealization of groups in general. We use them as a black box. We consider groups as something where we query operation of the group, but we don't know anything about the elements. We cannot generate new elements in this group. So it's quite an ideal model for groups, which is not realistic, but it's a well-accepted assumption to construct snarks. Okay, so now that we have an idea of the evolution of these proofs into more and more efficient one, let's decompose a little bit those properties and give a more specific definition. So we have snarks, which are, first we have snark with a G, which are, succinct. Like, as I said, the proof size should be independent of a NP witness, of an NP computation we want to prove. They are non-interactive. This is essential. We want to use them in distributed settings. And they are arguments. What hides behind this argument? So I'm usually abuse language and I'm saying proofs, but proofs is something that is guaranteeing soundness 100%. So we are sure that for a false statement, there exists no valid proof. For arguments, we cannot guarantee that. There exist proofs that verify for false statements. The thing that we know is that a computationally bounded prover cannot find them. So we have to guarantee that it's very unlikely that a bounded prover will get to cheat us, right? So there are arguments, and we can achieve only arguments if we want all these beautiful properties like succinctness, efficiency. Also, we want something more when we talk about snarks with K. These are arguments of knowledge. And arguments of knowledge mean that we have knowledge soundness. So we are not satisfied with knowing that the statement is correct. We want to know that the prover made the computation behind. So the prover has the intermediate values, has the witness to this statement. And this is captured by some artificial, somehow, formalization where we say that there exists an extractor that can get this witness from the prover. So this comes from this weird assumption I was talking about, this strong assumption. We want to make sure that the prover really did the computation and has the witness from. And this is knowledge soundness. And also we can add zero knowledge, as I said, to protect also the prover against the too curious verifier. So the proof will not leak any intermediate step or any secrets of the prover, other than this statement is correct. Great, so we have the definition. I'm taking questions if anything is unclear till now. Okay.
Yeah, I was just wondering earlier when you talked about the interactive proof systems, my understanding is that those were also like statistical. So by this definition, those were also arguments technically, right?
The interactive one can be proofs as well. There are proofs that are interactive. Yeah, it's mostly like this trade-off argument comes as a trade-off for succinctness. If we have a big witness and the proof size that is succinct, then we cannot build proofs. Like it's intuitively, we cannot compact something and make 100% guarantees. We are losing information in a proof about the whole statement because we cannot capture the witness there. We have to compress it very much. Yeah, so maybe this is the intuition behind why we cannot have proofs for some properties, but not necessarily non-interactivity, right? Okay, so now that we know what they are, let's see how they are built. So construction for snarks. We have a computation to prove. And instead of proving this computation, we will find an equivalent problem on polynomials, because polynomials are really nice and are magical, and I will show you why we prefer polynomials. And then we will prove that we have a solution to this, which means that we know the computation and the computation was correct. So this will lead into a snark where we need to generate a CRS, which is common for prover and verifier, and then the the prover will generate its proof, and the verifier is able to check and to accept or reject it, right? So this is how it works. Let's see how it's built. So first, in most of the schemes, in the ones that I will focus on today, the computation is a circuit satisfiability problem. We have the claim about any computation, f of x equals y. So we can write a circuit where the inputs are x and y, and this circuit is satisfied only if y is the result of f of x, right? And this circuit will be the one to prove. It can be Boolean or arithmetic circuit. Let's consider a generic circuit for now. So what is the prover able to do? Like naively, he can just take the witness, so all the valid assignments of this circuit that give 1, and send them to the verifier and make the verifier check this is correct. Unfortunately, we want something efficient to check, so the verifier should not read again all the computation. This is us repeating the computation, right? So this is too long. It's not succinct, it's not efficient for the verifier. Remember, Baloo is very lazy, has to optimize everything. So we need to remodel this kind of problem into something that is compressible in a way or another. And we find very nice creatures out there that are very, very friendly to compression, and those are polynomials. So instead of proving circuit satisfiability, we will prove that we have a solution to a polynomial problem, which is usually stated, this is a dummy toy example, but it captures very well how it works. So we have some public polynomials that are defined using some specification of the circuit. So they are really dependent on this circuit. And finding a solution P of X such that some division property holds, like some P of X is a multiple of P of X, like this kind of property holds, is like the solution to this polynomial problem. And finding this, it's equivalent of knowing the assignments that satisfy this circuit. So we forget about the circuit now. Mowgli has only to look at the polynomial problem and try to solve this. Either way, either it finds first the witness and then plug it here and it works, either it solves this, and this means that this is a valid witness also for the circuit. They are really equivalent. Great. So having the polynomial problem defined, this is a public thing, everybody can see it, we know what we want to solve, and Mowgli comes with a solution, a polynomial. A polynomial has as many coefficients, if it's written like that, has d coefficient for a degree d. So let's say we have degree d. And the way to convince the verifier is to send this solution. So to really send the polynomial, all the coefficients to the verifier. What we don't like here is that we didn't save anything. Like, as I said, the coefficients of this polynomial are really equivalent to the valid assignments to the wire. So it's long, it's not at all succinct, not efficient for the verifier. We just change the problem into something else, but as long as hard to verify. But what is nice about polynomials that make them appealing to use them in succinct proof is that we can do something else, something smarter than just sending the polynomial. So if we work over a field, the verifier can ask the prover just to evaluate the polynomial in one point, a random point S. So the prover should evaluate its solution in a point S and send back this very short, like independent of the degree of this polynomial, the evaluation of it is one field element. It's constant size, it's a scalar, right? So I am saying that some property it's preserved by evaluation in polynomials. So the property is that we wanted to check that P of X is a solution to this equation, quadratic equation here, for some public V of X, T of X. And of course, if we evaluate everything in S, this should still hold for the evaluations. So it suffices for the verifier to check on this evaluation P of S it's received. Everything else he can also compute. T and V are public. So yeah, here I should have done equivalent as well, not only one side. Yeah. No, actually it's good because if S is random, this is equivalent. If S is tailored, no, it's not. Okay, so this is what we had as an idea. What can go wrong here? So actually, yeah, the prover, like the verifier will just check this, right? So this means that the prover can also just cheat, and knowing S will compute those and find a Q that comes from a different polynomial that P of X, or not even, it's just a scalar that satisfies this kind of equation. So this will be accepted by a verifier, which is bad because this has nothing to do with knowing some real solution. A real solution is a polynomial. So we have to ensure that the prover really computes this proof from a polynomial P of X of degree D, for example. So yeah, what we will do? We will do something better. We'll hide the point S from the prover, who cannot now solve this equation. So we will just encode it. We'll call a generic encoding of S that for now just hides it. This is what we want from it. It's hard to open, to find out who is S. So now the prover has to solve this equation, but it doesn't know S, so has no chance to compute those. But can you see the problem here now? So he was supposed to send P evaluated in S. He doesn't know S. How he computes P of S? Like, yeah, he's in a bottleneck here. He cannot compute P of S without knowing S somehow. But sure, we have other properties of polynomials. So polynomials can have coefficient and can be computed by having all the the evaluation in one point can be computed if we have all the powers of that point up to the degree D. So instead of encoding just S, we will encode all the powers to D, and we will allow this encoding to be homomorphic, linearly homomorphic, in the sense that a linear combination with the polynomial coefficients of these powers will give an encoding of P evaluated in S. I guess everybody can see this, or scratch your head a little bit. So this is really a property of how an inner product is of consecutive powers of a point. It's the evaluation of a polynomial in that point. So what we will require is that we have nice encodings, they are hiding, and they are linearly homomorphic. This is not a big deal, like those exist in crypto. We are still not requiring a lot, but maybe we need something else. So for now, we have all the powers of S up to degree D. This is our common reference thing, the public information, the setup we need. And we have the proof pi, which is just the evaluation of P in S, which comes from a polynomial because we don't know those S's. So we really need to apply some coefficients in order to have this P of S, right? We cannot solve this equation. Okay, what we also need is like a verifier who receives encoding should be able to tell this is an encoding or is not just trash, right? So this is called image verification. Once we receive a kind of object, we are sure this is an encoding of something, not knowing what, but it's an encoding of something. It's a valid proof. And we also know, like as a verifier, we also need to check P of X times T of X equal V of X in the point S. So having this CRS, we can compute evaluation of V and T in S. And since everything it's encoded, because those are encoded, everything it's encoded is in these envelopes here, they are sealed. We cannot do this like by just looking at them. We need some extra property for the encodings, which is the quadratic root detection, which allows a verifier to check if such a thing holds or not. But keep in mind that one of the attack was the prover to solve such an equation and to find a valid encoding here. This is not possible because a very crucial assumption we will do on these encodings is that they are not only linear, but they are linearly only. So we cannot do anything else than like multiplication on encodings, we cannot. But a check that this holds, yes. This means just verifying proofs, but we cannot really multiply this and get a valid encoding of the product. This is not allowed. So great. Looks like this is the overview of how SNARK work. Okay, I really hide a lot of details under the rug, but those are very technical. This is really the basic idea, and I think it's quite clear. If no, just feel free to ask questions. So another point that I stressed at some point, and I didn't mention now, is that we need to extract from this proof. We need to know that the prover has knowledge of all the polynomial, all the witness, right? So how can we extract from a constant size? This is just an evaluation in one point. We should extract a full witness, so a full polynomial, so all the coefficients. So this is done with the help of this non-falsifiable assumption we rely on. We have some kind of assumption that says that given encodings of this kind, a prover that is able to compute a linear combination of them should know, like a new encoding of something should had produced this encoding as a linear combination of the given ones. There is nothing else possible. Like for the generic group model, this is basically in the model. Like you cannot generate new elements in a group without just recombining old ones. Nothing comes from the sky, right? So if you recombine the other ones, you knew what you did there. So we can extract this coefficient from the prover. So this is also a very high-level idea of what non-falsifiable assumptions are. So now the blueprint, what we have to keep in mind about SNARKs that we want to prove some computation, some relation, some statement, usually circuits, Boolean arithmetic, and we find a representation in a better way in order to compact this, to make constant proofs. So I totally didn't mention this for now, but we focus on these polynomial problems, which are called quadratic span programs, arithmetic programs, depending on the circuit. And some hardness assumptions and these non-falsifiable assumptions, which are completely necessary for the SNARKs. Great. So this is all I had to say about SNARKs. Let's go to challenges about adding privacy on top of this. So privacy means we want to encrypt. The computation provider will compute on ciphertext and give us a ciphertext and approve that the computation was correct. So as we said, this is our dream scenario. Unfortunately, there are not a lot of works that look into this. We had some early results that were very inefficient for 2010. For example, this was using some garbled secrets and fully homomorphic encryption. Both of these primitives are really inefficient in practice. So yeah, this is completely theoretic results, which is nice because it was the first. Then we had some verifiable computation for a function with a single bit of output. Same. This is from functional encryption scheme, things that we really don't know how to build in crypto unless we have some controversial assumptions behind. And more recently and closer to what I will present as a result today is this work from Dario Fiore and al., which combines fully homomorphic encryption and verifiable computation. Exactly what I presented before. The verifiable computation scheme will just plug on top of homomorphic encryption. But this only works for quadratic function in their construction in an efficient way. They have a generic construction, but it's inefficient. And it has no privacy for the outputs. So the prover also learns the results. So it loses a little bit of the guarantees of this encryption. Yeah, so this is actually the work we improved with the result I'm presenting today. So we want to go further than just quadratic function, and we want to separate the verifier and the client who has the inputs and who encrypts the inputs. So the one who encrypts should not necessarily be the one who verifies, should be publicly verifiable by anyone. And yeah, have more privacy maybe. But before going there, let's see what's the difficulty we encounter in building such schemes and why this was not very well explored. So already fully homomorphic encryption and ciphertext from fully homomorphic encryption are very complicated objects, are schemes that are not really very efficient, and they need to work on top of polynomials. So ciphertexts are polynomial in this ring, which is a ring of polynomials of coefficient integer modulo q, modulo some quotient polynomial. Just think of them as polynomial of maximal degree d, where d is given by this R polynomial. So we need to compute arithmetic function over polynomial. We will represent them as arithmetic circuits, but with polynomial and gates that are multiplication over polynomials and addition over polynomials, which are a lot of overhead compared to gates on scalars, right? So if we remember from school, adding two polynomials means adding all their coefficient pairwise. So this is linear in the degree of the polynomial for each gate. But multiplying two polynomials, it's not as easy. It doesn't work. It's a convolution product. So it may take a lot. We have better algorithms, but if we are pessimistic, it takes at least d square multiplication over scalars. So I told you that a prover knows how to build a snark over fields, over an arithmetic circuit that is defined over a field. Here Q should be prime. But we don't know how to do the same over polynomials. So what we will have to transform this kind of circuit over ciphertext into something over field elements, over scalars. And this means to add up all this. Like I made some maths here. For n inputs and n multiplication gates over polynomials, I just ignore all the addition that come from multiplication, which are a lot also. And I was optimistic about using very efficient multiplication of polynomial algorithms. And we still have this kind of overhead, which is dependent on the degree d of the polynomial. So this is scalar multiplication are very expensive for snarks. We really want to reduce them as much as we can. So this is a challenge for building snarks over such kind of circuits. But we have two approaches. And one strategy is the one I will discuss today, is like, first, it wants to hide the inputs even from a verifier that has the decryption key. So let's say that Baloo here will encrypt its inputs with respect to the secret key of somebody else, of Bagheera, who wants to have some results on his information, on his private inputs, but not his private inputs, just some statistic that doesn't reveal that. So this will hide by committing to these inputs the data also for the one who verifies the result. And what we would like to do and what we will achieve is that we reduce the computation over this to a standard snark on circuit on scalars that are an arithmetic circuit over field elements. So we want to avoid doing this by doing the same kind of number of gates, but over a field element. Okay, so this is our approach. And there is another interesting work on this, which will be presented at this research talk session in 1 month, I think, by Eduardo, my co-author, which just builds a new snark on top of rings. So these are not fields. All that I discussed before of how to solve arithmetic circuits, to build snark on arithmetic circuits, is for field, circuits over field. those are rings of polynomials. And yeah, there is a new construction of our rings with new assumptions, which with a lot of subtleties due to the fact that rings are not don't have all the elements which are invertible, so everything gets very messy. We fix everything that is messy, and we have this kind of assumption. But it's designated verifier only, so the proof returns to the same who has the inputs and the secret key to decrypt. So it's not that flexible, let's say. Great. But let's focus on, this will be a work presented later at Protocol Labs. Let's focus on the first work, which has this kind of scenario where we encrypt inputs, we delegate computation, the prover is able to prove the result, the ciphertext resulting from this computation, and some verifier can check this without having access to the inputs and not needing a verification key. Yeah, so it's publicly verifiable. This key is to decrypt, but we can also consider that someone who cannot decrypt can check a result is correct. I don't see the interest because the result is encrypted, so it cannot see it, but it can check it's a valid ciphertext for this circuit. And also, compared to the previous work, it treats also higher degree computation, not only quadratic functions. So as we said, if we just translate a circuit like that, polynomial addition and polynomial multiplication into scalar ones, we will have an overhead that depends on the degree of D. So we want to avoid this. We want to exploit the fact that we have polynomials. And I show you the trick for the snarks. Like once we have polynomials, we can always pick a random point and evaluate them to get scalars, to get constant size things, objects that are living in a field. They are civilized, they are nice to snarkifiable. You can just apply snarks on them. So we will transform this circuit, and each multiplication gate over polynomial will correspond to one multiplication gate over scalars. In this way, if we evaluate all the inputs in a random point k, we'll get an equivalent circuit with the same number of gates, but really light gates, not the heavy polynomial ones. So great, now the prover knows how to prove such a circuit satisfiability with classical snarks I just showed you. We only have to make the link. Who will believe a prover that this has anything to do with the initial circuit? And the link is exactly in the fact that all the inputs here should be, the circuit can be public, right? But all the inputs here should be evaluation of those polynomial in the same point k, right? I write it here. This is a secondary overhead, but it's minimal compared to what we had before. We have to prove that n polynomials of degree d were evaluated in this point. And we build this kind of proofs for polynomials. And the idea is to have something modular, what we call commit and prove methodology in proving system. So we compactly commit to the inputs on the polynomial circuit, and also compactly commits to the scalars in the other circuit. And we prove by the proof sigma that those are the results of the evaluation in the same point of those that are committed here. So we make a proof on top of commitments, never opening them, which is something quite common in crypto. So what are polynomial commitments and what are those properties of such a thing? So we have a polynomial, and committing to it means that we make a compact box that is hiding the polynomial and it's binding to this polynomial. So we cannot open later to something else. Once we commit to P of X, we hide P of X, which was a ciphertext. Remember, Bagheera could have the decryption key, but only seeing hiding commitments would not help decrypt this. And yeah, the server will just have to commit this. Great. So these are compact sites, and we will do something even compacted, even more shrinking than that. We will put all this polynomial together and commit them together to a bivariate polynomial. So how this works? We can we can store all the polynomials in one variable by using a second y variable. We store them by writing this like that with consecutive powers of y. We store the polynomial, we encode this kind of thing, and then we commit to a bivariate polynomial in a compact form. Okay, so we'll do this. We'll have one bivariate polynomial committed in a constant size commitment here, and one univariate. We shrink this together using one variate and commit it together in V of y. So V of y is doing the same thing, but with scalars here. It uses the power y in order to put them together in the same polynomial. And they are committed compactly. And now we just need to show that V of y actually is the evaluation in the point k. So remember that f of k was f, g of k here was small g, and so on. So we have to convince the verifier that we partially evaluate a bivariate polynomial in the point k, and we obtain a univariate polynomial in variate y. Great. So this is our sigma proof, which is a sigma protocol. I will not enter into details. It uses random oracle. It's non-interactive, and it's proving exactly this, that we evaluated. Here are the evaluations of this polynomial. So this proof should be composed with the proof with our favorite snark, with the most efficient snark to date, that will prove that these inputs committed in here are valid, are satisfying this secret, right? Are a valid statement. So we will use some previous work, which is called Lego snark, which allows for modular commit and proof, allows from this kind of combination. We have a proof with some commitments here. This is the statement for the first proof, and this will come as an input to the second proof. And this is completely possible. Great. So as a wrap up, we have compactly committing to polynomials, which are ciphertext. We have a bulky and heavy secret here. We just commit to it. We commit to a light secret here, and we show there is an evaluation in a random point relation between the two commitments. And then we show that we have a valid proof for the evaluation of this light circuit. And this, together with a commitment, will bring us to the correct evaluation of the initial secret of our polynomials. So this is our scheme. And just to conclude, let's see what will be the open questions and the points of improvement here. So as we said, it works for rings of polynomial, but we want to reduce them to a snark over ZQ, over scalars. And those work only for fields. All the theorems on evaluating a polynomial in a random point and things like that are good if Q is prime. So this is not corresponding with how FHE are using this kind of ring polynomials. They usually split Q in a product of primes. So we can find FHE, but they're very inefficient if they're working on over this. It doesn't support other operations that are vital for FHE to be optimized, like rescaling, bootstrapping. No, it doesn't support all this, unfortunately. But it is very modular. It has commit and proof composition. As I said, you can plug all your favorite snark. If tomorrow there will be a new super efficient snark, you can just put it there and use it to obtain a better protocol. And it's zero knowledge for inputs and for computation. So the verifier should not see the inputs. It's just convinced by the results based on some commitments. The other work that will be presented in a couple of weeks, it's better adapted for any kind of arithmetics over rings. So this can be any ring, not specifically with the field polynomials over a field here. So Q cannot be can be any integer. This means more efficient FHEs. It supports subcircuits for special operation, modulo switching, notably, but we are confident we can design other circuits if we really try hard. And it's designated verifier only, so it has its downside, and it's not hiding the inputs because it's requiring the same verifier as the one who encrypted them, so it doesn't have to hide them. And it's not zero knowledge, but we are also trying to make it zero knowledge. I think it's a quite easy transformation. Okay, so this will conclude my talk, and thank you, and happy to get questions from you.
It's really cool. Thank you. Been a while since I've looked at any of this, so these questions might not make any sense. But what was the problem with functional encryption? It was using LWA. Is that the?
It's the functional encryption for any function. It's requiring indistinguishable obfuscation. So we know how to make function encryption for easy function like inner product or addition or even quadratic. But everything that is over quadratic, we fall into this necessity of assuming indistinguishable obfuscation, which is more and more popular these days. Maybe we can construct it now, but still it's theory for now.
Yeah, because my recollection was that FHE, like by hiding like all of the information, you ended up making some of the circuits like super inefficient, right? Like if you tried to do like binary search, like if you try and search both directions of the tree, then you've made it like an O of n search instead of a logarithmic search kind of thing.
So maybe I missed a point. So what is this? How is this related to the functional encryption?
Functional encryption allows you to decide what information you're leaking, right? Whereas FHE like hides everything.
Yeah. But functional encryption also doesn't allow to work with ciphertexts themselves. It gives a key that decrypts to that information. So it's all the power of evaluating a function. It's in a key. You cannot just use, like in fully homomorphic encryption, ciphertexts are translated in another word where you have the same kind of operation as in your original clear text. And this is the power. You do the operation in the other word, everything is hidden. And this reflects what could have happened in the real world over clears. Functional encryption is decrypting using a secret key to a function of the input instead of like decryption just decrypts the identity function. You get back the input that you encrypted. Decryption in functional encryption is more specialized. You decrypt a function of the input. So this is one of the reasons it's really hard to imagine how a big computation can be achieved by using a single element, a secret key, right? Everything it's actually in the secret key that decrypts to a function. So yeah, they assuming indistinguishable obfuscation it's easy because that's a heavy tool. The decryption key is just the obfuscation of the function, right? And you get the result. So I'm simplifying. I'm really mean doing this, but kind of it's a straightforward way to do it. Like obfuscating the function you want to evaluate, making this the secret key directly gives you what you want.
Okay, thanks.
Okay, cool.
I had another question. At some point in the slide, you mentioned you commit from all these variables to a bivariate polynomial. Mm-hmm. And how do you make sure that you really take the correct polynomials to create this bivariate one? Like why can I not use another polynomial instead of f or g or p or q?
Like you mean not the one that okay, yeah, I see your question. Not the one that Baloo sent, the client sent. Yeah, that's a good question. That's a good point. So actually, these steps of committing to the inputs is also done by the client, by Baloo, if we want to trust this. You're right. So, of course, a approver can just have fun of changing those, and changing those, it still has a valid proof, but the results will be with respect to other inputs. So in order to make sure that the inputs come all together from the same source, yeah, this commitment phase should be done by the client who outsources the data encrypted. Should also outsource a commitment to this data.
So we trust the client in some sense.
We should trust someone at some point, right? Like the client is contributing with inputs, and if it has interest to find out the computation result, then it should put the right inputs.
Yeah, makes sense. Yeah.
Yeah, it depends on the scenario. I agree that, yeah, you have a level of trust somewhere. Yeah.
Okay. And just to make sure I understood, the prover does have access to all the coefficient of F, G, P, and Q, or it does not? I was not sure about this.
Yeah, because those are ciphertext, so you see the ciphertext. They hide real data behind, but these are ciphertext.
So he has a coefficient of all these polynomial, and he has a commitment done.
Yes, yeah, exactly.
Thanks.
Folks, thanks for tuning in. Our next talk is Tuesday, February 9th at 1700 UTC. It's from Sarah Azubi, who is a consensus researcher at Protocol Labs. Her talk will be on tools for game theoretic models of security for cryptocurrencies based on a paper that came out last year. If you're watching on YouTube, please join our mailing list. You can specify the types of emails you want to receive, so you don't have to get any emails you don't want, but we use this list to advertise future talks, as well as research funding opportunities and other important news from Protocol Labs research. You can subscribe in the footer at research.protocol.ai. Remember to hit the like and subscribe buttons and share this video. If you want to suggest a topic or a speaker, there are instructions on how to do that in the description, or you can email us at research@protocol.ai. Thanks for joining, everyone. We will see you next time.